Hello, good morning everyone. My name is Ziad Iqtari. I am PhD student at the Laboratory of Mechanical Engineering in the National School of Engineering of Monastery. I have the pleasure to present my works entitled Design of New Ring Hoop Shear Test for Mechanical Characterization of Tubular Materials. Here is the plan of my presentation. First, I began with an introduction, then specific test for characterization on problematic, then a new test, the Ring Hoop Shear Test. After that, the experimental methodology, then the results and discussion, and finally the conclusion. One of the sources of anisotropy in tubes are the forming process such as cold-hot extrusion or rolling welding due to the texture characterized by a preferential grain orientation. Consequently, the plastic flow is not the same at each orthotropic direction. Assessing the anisotropic behavior and the mechanical properties of tubes is a challenging task. This is essential for engineers to have reliable simulation of complex forming process such as hydroforming and bending. So in this context, Iqtari and al. Have conducted uniaxial tensile test and ring hoop tensile test to obtain the coefficient of anisotropy of Langford and the plastic flow along the axial direction and the hoop direction. Note that the specimens employed in this test are optimized and cut directly from the tube without any mechanical transformation to preserve the initial property of the tube. The problem here is how to assess the anisotropy in the direction 45. What is done in literature is, for example, the tensile test on a flattening arc cut at the direction 45 made by Zribi and al., or a ring hoop tensile test on a ring cut at the same direction made by Musavi and al. In 2018. But those two tests are not very recommended because the difficulty to extract the specimen and the direction 45, and then the flattening causes pre-strain on specimen. As an alternative, it has been established that the shear test is a very interesting one for characterizing of sheet materials and could provide us an information about the R45 Langford coefficient. However, until now, there is no shear test dedicated for tubes. So we propose in this work an original shear test on a ring specimen. This specimen has double shear zone between 4 notches. Another mechanical tool is designed and manufactured to handle the specimen during the test. The Ring Hoop Shear Test specimen is maintained concentrically and blocked between the insert and the support of the loading device. The plunger element is gripped to the free central area of the specimen with the screws. The upper grip of the tensile machine is fixed to the plunger element and compression loading is applied. The shear stress and the shear strain are given by the following equations. Assuming orthotropic symmetry, the vector 1, 2, 3 are respectively the axial direction z of the tube, the hoop direction theta, and the thickness direction r. The theoretical shear stress along the axial direction and according to the heel 48 is written in the following equations. The Langford coefficient 45 will be identified by matching the theoretical shear curve with the experimental one. The numerical model of the ring hoop shear test is mainly composed of the ring shear specimen and the plunger, which is constrained to the central part of the specimen. A reference point RP is assigned to the top of the plunger to monitor the reaction force replicating the experimental procedure. The ring is measured using 3D 8-node continuum element with reduced integration and hologless control, while the plunger is measured with 3D bilinear 4 nodes rigid quadrilateral elements. A refinement mesh is applied on the shear zones with a dimension of 0.5 mm. The ring hoop shear test was carried out using an universal instrument tensile machine in compression mode at a speed of 1 mm per minute. Due to the curvature of the surface of the specimen, 3D stereo digital image correlation using RMS system is used to monitor the full field strain in the shear zones. A random black speckle pattern is applied on the specimen before testing in order to enable strain data acquisition by the system. Let me present here the experimental results. This figure shows the shear strain contours in the shear areas measured using DIT. One can see the quasi-homogeneous strain field in the vicinity of the shear areas with expected local edge effect. From the acquired strain field, the representation of the major strain versus the minor strain shows that the proposed shear specimen undergoes a shear stress state with a strain ratio close to -1. On the other hand, from the experiment uniaxial tensile test and ring hoop tensile test, we obtain the coefficient of length for R0 and R90. The results shows that the aluminum alloy 60630 is anisotropic. The identification of the Hales 48 anisotropy parameter N is obtained by minimizing the difference between predicted shear curve and the respective experimental tau gamma curve using last mean square method. Note the experimental length for coefficient R0 and R90, the R45 is then deduced. This figure shows a good match between the experimental, the analytical, and the numerical shear curves. In addition, the numerical results of the ring hoop shear test shows a homogeneous stress state in the double shear area of the specimen. Finally, an original ring hoop shear test is developed to carry out simple shear test on ring specimen. A specific mechanical device was designed and manufactured to handle the shear specimen to be mounted on a universal tensile machine. Experimental tests using DIC and numerical simulation show a homogeneous shear stress state in the shear zones of the specimen. The anisotropy length for coefficient R45 and the mechanical behavior of the aluminum alloy 6630 have been accurately determined from the NUE test. Thank you for your attention.